Alright, this video is going to be on the definite integral. So the definition of the definite integral is if f is a continuous, well, if it just is continuous. If it is continuous and defined, on AB, so that means this closed interval AB is part of its domain. Those are x values that can work. And it's divided into n subintervals of equal width. Then we're going to say that this notation equals the limit as n approaches infinity of delta x using the summation from 1 to n of f of x sub I. So with the last video we learned about this notation. On this video we're going to learn this notation right here. And they mean the same thing. So today we'll be going back and forth between the two different types of notation. So this is what we use for our integral. The number up here is our upper bound limit. So that was the b, the upper bound of the interval. This is our lower bound limit. And then f of x dx is called the integrand. And you're going to say dx if x is the number that you are integrating, or you would use y if y was the value that or the letter that you were integrating, or just whatever variable you're using. So this is the variable to integrate. And then equals the limit as n goes to infinity and like we talked about yesterday, this is the Riemann Sums, and that was when we were using rectangles to find the area. So that's where we had one number being multiplied in the front, and then in parentheses we had a bunch of different numbers being added together, and those numbers being added together were whatever you got when you evaluated the function at different values. So this notation right here, or what we're looking at as n goes to infinity, so if you had an infinite number of rectangles, this is how you find the exact area under the curve. So this is not where we're drawing 4 triangles or 6 triangles. Rectangles. This is when you're doing infinitely many. So this is the exact area under the curve. All right, so here are some examples. And we're going to do just a couple, kind of going back and forth with the two different types of notation so we can see how they work. So our first example is we are going to express this limit as an integral. So when we express it as an integral, we're going to go ahead and say the upper bound, which was pi, to the lower bound, which was 0. And then here, we just write down what our function was, and our function is just what we would have had without plugging in the x sub i's. So it'd be x to the third plus x sine of x, and then we put a dx on the end. And that's it. We've written it as an integral, and so we're done. Next, we're going to go ahead and write this integral as a limit of sums. So this is where we take this information and we do it back into the other form. So we're going to make it look like this. So we have to know what our delta x is, and that is b minus a. So b minus a divided by n, which gives us 3 over n. And then we have to figure out what our x sub I is, which is this part multiplied by I plus the number that is used for the lower bound, which happens to be 0. So that's 3i over n. So now we can say the limit as n goes to infinity of our delta x, which we said was 3 over n. And then we've got the sum from 1 to n. And then we take the function and we replace the x's with the 3i over n. So that would be 3i over n to the third minus 6 times 3i over n. So that's how you write it as a limit. Next, I'm actually going to put this on my next sheet of notes because it takes a little bit more work than the lines I've got left. So next we're going to use the problem that we just did, and we're going to evaluate the Riemann sum. So we're going to evaluate this equation right here. Evaluate the Riemann sum for that function using the right endpoints from 0, 3 with n equals 6. So we're doing the Riemann sum, basically saying we're using 6 rectangles. So my delta x, like we said before, is 3 minus 0 for b minus a, and we have 6 subintervals, and so that's 3 6 for each one, or we could say 1/2. So that's how wide each of our intervals is going to be, or how wide each of our rectangles is going to be. And so then if we look at our x sub i's, or the numbers that we're going to be plugging into the function, we're going to start at a value of 0. So, or we can go ahead and write out the formula for this. It is 1/2 multiplied by I plus the lower bound of the number. So that means that for our xi's, we are starting off at 0, and we're going up by 1/2 for each one. So 1/2, 1, 3/2, 2, 5/2, 3. And then we are using the right endpoints. So I'm going to say the width of each of these rectangles would be 1. And so the first rectangle, the width happens from 0 to 1/2. And the right endpoint would be the y-coordinate, or the height of the rectangle would be whatever I get when I plug 1/2 into the function. So I'm going to say f of 1/2. And I'm going to write it this way because I don't want to have to write 1/2 to the third minus 6 times 1/2. That's a lot more to write. So that's our first rectangle. Our second rectangle would have a width from 1/2 to 1, and then the height of the rectangle would be figured out by plugging 1 into the function. And then we would plug in 3/2 to the function, and then we would plug 2 into the function, and then 5/2, and then 3. And this, we're actually going to look at how to plug this in on our calculator, because this looks kind of terrible to plug in if you think about having to plug all those numbers in and keep track of everything. So here's what I want you to do on your calculator is we're going to actually plug this into y equals, although we're not going to graph it. We're just going to type x to the third minus 6x. like this, and then go ahead and quit. So get out of that and just get to your normal calculator screen. And now we're going to type this in. I've got 1/2 parentheses. And the way that you can type in f of 1/2 is if you hit the vars button right here. And then we're going to go over to y vars because f of x is another way of saying y. And we're going to use function, and y1 is where we just plugged that in. So we're going to say that of 1/2 plus, and then we're going to do it again. So vars, go over to y vars. And it seems tedious right now, but I promise it will, when you get fast at this, it'll make your life a lot easier. So vars, y vars, plug in 3/2, vars, y vars, 2, vars, y vars, 5/2. And so when we add up all those little areas to find the area under the curve, we're going to say that is negative 3.9375. And we used a Riemann sum, which means we broke it up into little rectangles. And so this is not an accurate measure. This is just kind of an approximate or a guesstimate. All right, the next example says to write this integral from 2 to 5 as a limit. So first we're going to look for our delta x, which is b minus a divided by n. So that's 3 over n. And then our x sub I would be that multiplied by I plus our lower bound. And then we can go ahead and write it as a limit. So as n goes to infinity of 3 over n, we've got I equals 1 to n, and then we just have to take this part right here, the 3i over n plus 2, and plug it into the function. And that's it. Okay, last example on here. We're going to express the following as integrals. So the first one so we have to figure out what our boundaries were that helped us get to these answers. So I know that this is my delta x, and the way that you figure out your delta x is you do b minus a over n. And so that means that we somehow got that to equal pi over n, so we must have subtracted two things that subtracted to pi. And then we know that our xi is what we get when we take that b minus a over n. That answer gets multiplied by I, and then you add the a value on the end. So over here, we know that this was pi over n, and we know that this answer right over here ended up being pi times I over n, and so that means there was nothing on the end to add. They just added 0 on the end. So when we write this as an integral, I know my lower bound was 0, and I know that if I had to do something minus 0 to get pi, then the something I must have subtracted 0 from would have also been pi. And then if you look up here, this part is what gets plugged into the function, so the function must have been x to the third plus sine of x. dx. All right, here we're going to do a very similar problem. We're just going to switch things up a little bit on it. So here you can see that we had the part from the delta x written right here with a little I on it, but this part right here must have been that a value. So our a value here is pi, and that means if we did b minus a equals pi, then we must have had 2 pi minus 1 pi equals pi to do that subtraction. So that must be 2 pi. And then our function is the same here. It's still x to the third plus sine of x.